Hey guys, as you probably know, my name's Austin, Jacob and DJ are behind the camera, and today we're going to learn about satellite motion. Now see, satellite motion is a funny thing. You ever notice what those bright things are up in the sky? That's what I'm doing. I'll be walking outside and I'm going to see, what are those bright things up in the sky? Because I know they aren't stars. You know, funny thing, when you make a wish on a star, it probably already exploded, so you're actually making a wish on a dead star. Oh, true, I'm sorry. Anyway, we're not talking about stars today, we're talking about satellites. Satellites are things. Then, you know, the funny thing is, they're not the satellites we always think of, you know, with the solar panels and everything. Sometimes they're just moons. You know, like Jupiter has a lot of satellites, but they're just moons. And they just spin around bodies like the sun and other planets. It's weird. So we're going to learn about those, how they move, and why they move the way they do. We're going to do some math, going to do some concept, and then we're going to have some practice problems for you guys. That's going to be fun. You know, I like practice problems. I don't know about you. You probably don't. But we're going to do it anyway. Come on! Alright, thank you, man. Okay, so now we're going to get into actual satellite motion. Let's put a satellite up here. There we go. Pardon me, not drawing, it's not great. Anyway, okay. Got the little solar panels on the side, and it follows this path. It's like a really big guy through the satellite so fast that it goes around the Earth. And of course, it's out to the atmosphere, no mountains, no friction, obviously. Now, as it's going, it travels at a different speed than something that would be going in a straight direction. Kind of like throwing the ball and it hits the ground. It moves in a circle, and it always moves in a circle. So, ace of C. But, this still has force. And this is demonstrated by the equation ace of C equals mv of t squared is tangential velocity. Because even though the satellite maintains the same speed, it's still accelerating because at each point it changes direction. So yeah, well, it's over here. Tangent line showing its velocity right there, right there, right there. See, they're all pointing in different directions, showing that this is still accelerating, even though it may not change speed, because the vector for velocity includes direction in it. So ace c over v sub t squared over t describes tangential velocity. And doing this, we can measure the speed. For example, all right, let's say that was close to Earth orbit. Another satellite. And it's really easier to demonstrate this with the merry-go-round if you want to think of it that way. All right. So we have a satellite. Now, this satellite travels less distance. And let's say that at each point in this satellite's path, it's at the same point this satellite is. So when this satellite's here, so is that one. So this satellite travels more distance in less time. Therefore, this satellite's actually moving faster than that one, even though we can't see it. And centripetal force is what we just use to describe why the satellite wants to be pulled into Earth. First of all, we got to get something in our head. Inertia, and this is a misconception I had before I started. Inertia, right, I, wants the satellite to go out. So, satellite's over here. As it's traveling, it wants to keep on going in that direction. However, if we do F of C, centripetal force in this case is actually gravity, and gravity's trying to pull this satellite into Earth. Inertia's trying to get it to go that way. Think of it this way. When you're in a car and you make a really sharp turn, the car wants to move, and then you go against the door or the console or wherever you are, because your inertia is keeping you from going. It keeps you from just going inside and staying in a perfect circle. However, the car stops that. And the centripetal acceleration is like, no, you're not going anywhere. And then it wants to pull you inside to the center of where the car's turning. So like if it's turning this way, center is right there. And then we think of this the same way with satellites. Earth, in this case, Earth's gravity is actually pulling this in, inertia's out, and because of that balance of that equilibrium forces, it just maintains its perfect circle. Pause it because I gotta think something else. Alright, so we did all this math and stuff, but let's get down to the nitty gritty. Who the crap cares about what satellites are doing in space? Well, let's put in perspective for you. Let's say we have a satellite dish on my house. You know, my name's Phil Shifley. And then I draw. Hold on. Alright, so let's say I'm Phil Shifley here. Got a little satellite dish. This is going to be a little bit bigger. Okay, and it shoots this satellite. Now you look over here. Hold on. Trying to get okay. Alright, so we did all the math and stuff. Now, most people don't care about the math. So we're thinking, why the crap should I care about satellites in orbit? Okay, well let's think about this. Alright, so I'm Phil Shifley. I just bought DirecTV. I bought this fancy new satellite. It's that big, and it's shooting out into space. Now, obviously, most of us know how satellite TV works. It's a satellite. Over here. Now, let's draw second Earth. Okay. Now, alright, so it's nighttime, you know, I'm trying to watch TV at 3 a.m. Big satellite. Satellite's moving slower. Satellite's all the way over here. Now, how am I supposed to watch TV if the satellite's right here and I'm trying to shoot a signal out into space, you know, hitting aliens or something? Well, people move the speed of the satellite so that, and we discussed this last class, the period of the satellite isn't always the same even though it might be orbiting the same body. Because, well, just don't fret, you can get whatever speed you want. So, alright, satellite's over here. We can get the satellite, and we, you know, of course, people that work in DirecTV or wherever, we can get the satellite to stay right above where the Earth is. So, when the satellite's over here, so it's a dish. And then it's always pointing directly at the satellite. That's why when you have bad weather and you have satellite or something, the signal cuts out because it has to be pointing right at that satellite. And whenever, you might notice whenever you go outside and you look up at the stars, most of the satellites, you notice that they're all in the same place most of the time. That's because where the satellites are usually pointing at satellite dishes. They're not a bunch of spies trying to get us. There are some spot satellites. But I'm not covering that today. Okay. Oh, more math. I'm just kidding, guys. This isn't that much math. Alright, so I'm just going to break it down for you all. Satellite motion likes to use a lot of different equations, and there are a lot of big equations. So, what we got up here, just look at these four up here. Alright, so we have Newton's law of universal gravitation. It's okay. Then someone else teaching you about that. We have centripetal acceleration, tangential velocity, and centripetal force. Alright, so let's just break it down. Alright, let's start out easy here. We got F equals mv squared over r. Force equals mass times velocity squared over radius. Now, we sub in Newton's universal law of gravitation for force. So we have gravity times the mass of the orbiting object times the mass of the object being orbited over radius squared equals mass times tangential velocity squared over radius. Now, after I break it down, it's really not that hard. Alright, so we cancel out the r's, so, and we multiplied, so the r goes up here. So we have mass of 1, or the mass of the first object, times v squared, times r, equals gravity times n1 and 2. Mass of first object, mass of second object. Now because we have mass over here, we cancel those out, as you can see I did here, and then we make another sub, v squared, and then we sub in v here, so it goes over there. So it's 2 pi r squared over t, and of course we actually just learned that in a class a few minutes ago. So that's squared times radius equals gravitational constant times mass of the second object. Alright, so we squared that, and then it starts to get really weird. The crap gets weird here. Alright, so we have 4 pi squared r cubed, and of course all I did was square everything, over gravitational constant times mass equals t squared. Now, you just take the square root of everything, alright, square root of t, square root of all that. So we have, because you can take the square root of 4 pi squared, you move that outside, so that's just 2 pi. And then the stuff you can't take the square root of, you just put under the radical equals t. So what we get by combining all these equations is that the time it takes for a satellite to orbit something is really 2 pi times the radius between, or the radius of the planet, or whatever you're orbiting, tells you how big it is, over the gravitational constant times the mass of the satellite.